Our final speaker of the day is Michel Pain, who will talk about the height of weighted recursive trees.
Thank you for the introduction. Thanks to the organizers of the workshop and of the whole semester and the CRM staff as well. So yeah, I'm going to talk about a joint project with Delphin Sénizergues, which is a postdoc at UBC. Okay, it's about a probabilistic model. And the fact that I'm a probabilist will be clear not because I write 1/2 Laplacian, but because I don't write any Laplacian at all. So it's a discrete probability model, but okay, connected to things we have seen so far. Okay, so let me introduce the model. We fix weights Wi are non-negative. It's a sequence of weights. It's considered as fixed. And then we build trees recursively. So we start from the first tree, which is T1. And T1 is simply the vertex 1. And then I will grow my tree by adding vertices, one after the other. So I will add vertex number 2, vertex number 3, vertex number 4, so on. And the way I add my new vertex, the way I add here, for example, vertex number 6, is I choose the parent at random in the tree, and I choose at random proportionally to the weights. So here, vertex 1 actually has a weight W1, vertex 2 has a weight W2, and so on. And I will add, I choose at random vertex according to the weights, and I attach vertex number 6, and so on. So okay, the rule is the probability. How do I attach vertex number n plus 1? I attach it to vertex number I, given the tree up to step n. This probability is equal to the weight of W of vertex I divided by the total weight of the tree. So that's my notation. Capital Wn is the partial sum of the weights. Okay. Questions about the model? Okay. So it has been introduced by Borovkov and Vatutin. 2006. And it's a generalization of the uniform recursive tree, which is obtained just by taking all the weights equal to 1. The URT, I will call it, the uniform recursive tree, which is defined by taking all the weights equal. Each time you add a vertex, you pick the parent uniformly in the tree. Okay, and here we want to allow some heterogeneity in the tree. Some vertices can have a very large weight, some other small weight. You can think as the sequence Wi as tending to infinity or tending to 0. Okay, and the question is, what does it change? And my main question will be, what does it change about the height? If you're a probabilist, you can also pick the weights randomly. But, then you fix them and you do the procedure like this. So, okay, I will always consider that they are fixed, but you can pick them randomly and then choose that almost surely that satisfy the assumption of the theorems that I will state. Okay. So okay, for me, the motivation here is really how far can we go with the weights without losing the universality of the behavior of the uniform recursive tree, and what happens when we go outside from this universality class. But there are motivations which come from the connection with other models. So it's a quite simple model, so it arises in different contexts. For example, it's related with preferential attachment trees. It appears in some random walk with random relocation. Okay, I don't want to spend too much time on this, but I would be happy to answer questions about the motivation. And also the literature, there are several results which are more about degrees in the tree. What is the degree of a fixed vertex? What is the maximal degree in the tree? Or what is the degree distribution in the whole tree? I won't talk about it neither, but there are several papers on the subject by Michel Pain, which is in the room, and other people. Okay, here I will just focus on this question. Okay, I will start by stating some first properties of the tree. And the first fact is the following. The height of the vertex number n+1 has the same distribution as a sum of Bernoulli random variables. So the BIs are independent Bernoulli random variables, and BI has the distribution Bernoulli with parameter Wi over capital W. I will prove this first fact, which is the proof is really simple, and I find it's a nice first result to have some intuition of what the tree looks like. So, okay, what is the proof? It can be summarized by this sentence: look backward at the lineage of the vertex n+1. Okay, so I start. So what does it mean? I start from my vertex n+1, and my question will be, which vertices are in the path which leads to the root, the vertex number I? And if I know how many vertices are here, I know the height of n+1. Okay. And okay, the main idea is really to look backward. I start from here, and my first question is not is vertex number 2 in the past, but rather is vertex number n in the past. So the probability that vertex number n is in the past, it's the probability that when you attach vertex n+1, you attach it to vertex number n. So it's probability Wn over capital Wn. This part is easy so far. But now I look at the next one. I want to know if n-1 is in the path. And I will distinguish two cases. First, given that n is in the path, or given that it's not. Okay. So two cases. So first, let's say that n is in the path here. And I want to know if n-1 is in the path. Then it means that n has been attached to n-1. So the probability is Wn-1 divided by capital Wn-1. Okay, it's the probability that vertex number n has been attached to vertex n-1. And otherwise, it's the probability that first you know that n is not in the path, and now you want n-1 to be here. So it's the probability that n plus 1 has been attached to n minus 1. Okay, if you write it quickly, you will say that it's the weight of n minus 1 divided by the total weight, which is capital Wn. But actually, you're working given the fact that it has not been attached here. So somehow you know that n plus 1 has to be chosen among the point where you attach it. It has to be chosen among the others. So actually, you're still dividing by capital Wn minus 1. Okay, it's the same probability in both cases. So that's the proof. You go on like this, and actually, the probability that I is in the path, it's Wi over capital W. Questions about this? What can I say from there? So that's the end of the proof. I will define an, which is the sum of these ratios. So it's both, it's the mean height of n plus 1. And it's also approximately the variance if actually the variance here will be so the true formula is that it's the sum of this ratio, but times 1 minus this ratio. If weights are not too big, so if at each, okay, I will always work in the regime where the weight of a new vertex is always negligible with respect to the whole weight of the total tree. So this will be approximately 1. So we'll work in a regime where it's always more or less an. Okay. So far, I'm working in this regime. So what you can expect is that more or less the height is normally distributed with mean an and variance an. And okay, there is a more precise result by Delphin, which says that the whole tree has this profile. So okay. The tree has a profile which is looks like a, so it's a Gaussian profile with mean an and variance an. That's the moment where we look at some pictures. So that's the uniform recursive tree. We stay here. So the first vertices are in blue. First vertices in the tree. So some of them are quite high. And then along when I add vertices, there are more and more green. So the green vertices are the ones which have a label which is close to n, and the one which have a label close to 1 are in blue. And here, so that's the uniform recursive trees. All my weights are equal to 1. In that case, the total weight, okay, it's equal to n, and an is growing like log n. So what Delphin is telling us in his results is that here centered at level log n, with the variance more or less square root log n. Yeah, with a standard deviation square root log n, you see the Gaussian shape. Okay, here you can see it looks like a Gaussian. So what I've not said is that it's represented the distance at each level, the distance between vertices is exactly the same. So if it's that large and then that's large, it means that you have twice many particles. You can really see the number of particles at each level just by looking at the width of the tree at each level. Okay, and Delphin also proved that here the height at the first order, so actually this for the uniform recursive trees, it was known a while ago, but it proved that it's always a constant times log n. So okay, let me just add this here. So okay, in which regime is Delphin? Yeah, I forgot to say something important, which is Delphin here is in the regime where Wn behave as a constant times some n to the power gamma for some positive gamma, plus something smaller. So the total weight of the tree is growing polynomially fast. And then in that case, an it's more or less gamma times log n. And Delphin proved that the height of the tree, almost surely, it's asymptotically equivalent to some constant times gamma log n, where C1 is a constant depending on gamma, which is explicit, and which is larger than 1. So, okay, AN is giving you the center of the tree, where most particles are, and the height is some constant multiplicative of this. Questions about this? I will show other, yeah?
Do you get this constant just by a union bound, well, by a first moment calculation with these polynomials?
Yes.
Okay.
Exactly. That's the so I will come back to this, but yes. So here I take weights which are growing so my weight at times I is I to the 9. So in that case, the weights are growing very fast. So my first vertex, no one will get attached to it again, and so on and so on. The beginning of the tree is kind of very thin, but you still see the Gaussian shape which appears here. So this is approximately AN again, and the width is square root AN. Okay. And again, the height is some constant multiplicative of this. I can also take a weight which grows polynomially fast, but in a way which is so not as fast as linear. So here I take a square root n. In that case, you can see that, okay, the first vertex, for example, it will have many children. Oh, I made everything disappear. Okay, sorry. The first vertex has many children. But still you have the same behavior, which is at some AN, you have the center of the Gaussian shape, and that's it. Okay, so on the questions that we are asking here, these trees have the same behavior, even if you look at some local properties, for example, degree of the first vertex or things like that, the behavior is completely different. But for the height or the profile, they have the same. Okay, and we will also discuss cases which are not included here, where Wn grows subpolynomially. So for example, here, I take the weight Wi, which is 1 over I, then the total weight grows only like log n. And what we will see, so it's not included in Delphin's results, but you will still see probably a Gaussian shape, which is centered at AN, but now AN is some log n. And we will see that the height of the tree, it's much higher, it's at log n over log n. So here it's not true that the center of the profile is proportional to the height. You kind of have a very low body with many particles, and then a very thin profile going quite high. Okay, and finally, a very degenerate case. If I take the Wi's, which are like 1 over I squared, then of course I have a finite limit for the total weight. The total weight is converging. But still, okay, so my first vertex is having many children, but still the tree is growing, and it will go to infinity and at a given speed that I won't give you right now. But of course, here you cannot expect a Gaussian profile. The profile is here, and it's quite discrete. Okay. It's about this picture, or otherwise I will stop. Okay. So back to math. What is the type of proof that Delphin used in his paper? He's using proofs inspired by branching random walks. So maybe one thing I want to say about it is that it's not clear that, I mean, I said the vertex number n is distributed like a normal distribution. It's not enough to know it for the profile of the tree. Of course, there could be some correlations and so on. And you need some arguments to state that actually the profile is indeed Gaussian. And okay, so I will here present a branching random walk analogy, which is helpful to understand the results afterwards, at least for people who know branching random walks. Okay, so what is the analogy? It's not rigorous. I'm not pretending anything like this. It's completely heuristic, but okay, I want a branching random walk at time t, and time t, because a branching random walk, so what is a branching random walk? Maybe I can repeat it briefly. Here I have time, and I have a particle at 0, time 0, and each particle has a given number of children, a random number of children. Each child is doing a jump randomly, and so on. Here, so a branching random walk is growing exponentially fast in the number of particles. Here I'm growing linearly, so I have to do a time change. The time t will correspond to times log n in my tree. So that, and I will have mean number of children equal to e. Sorry. At time t, I have roughly exponential t particles, that is n. In my tree, I have n vertices. So. Okay. And now, what is the jump distribution? So you know that the trajectory is given by this random walk, but which is inhomogeneous. I mean, weights are not always the same. And if you want to have a one jump in the time of the branching random walk, you need to cut between two times. So jump distribution, it's reasonable to assume that it's the, so at time s, I would say. So for now, there is no reason that the jump distribution is the same at all times, actually. The jump distribution at time s, I want it to be the sum between exponential s and exponential s plus 1. So in my tree, I'm between times s and times s plus 1. So it's more or less in the trajectory here, it's the part where I sum vertices between exponential s and exponential s plus 1. See Pascal, which is not happy with it. So why not? No, you're not.
You haven't finished, so.
No, okay, really. Now I want to see my particles here. Of course, it's not rigorous, and I don't think there is any way to make these connections rigorous. It's really to get some intuition about what's going on. And I say, okay, I need to change time because my tree, I want it to grow exponentially fast. So I do this change of time. And then when I look at the trajectory of one particle, typically at time t, I know that its trajectory from the very beginning was this sum of Bernoulli random variables. And I want to say I can cut it into pieces. And between times s and s plus 1, actually in my tree, it's between times exponential s and times exponential s plus 1 of this Bernoulli random variable. Okay, maybe you will be more convinced afterwards. But okay, then you can, it's a sum of Bernoullis, you can approximate it by a Poisson random variable, which is the sum between of the parameters between. If these quantities are all small, you can use the Poisson approximation for the sum of Bernoulli random variables. Okay, and this is approximately the same. This is exactly the same actually as okay. Let's just put as a Poisson random variable, which is I take the sum up to times exponential s plus 1 minus the sum up to time exponential s. So I remind you that n was this quantity. So here I just have the difference between two values. Okay, let's keep it here. And let's do an example. So, okay, Delphin was using branching random walks techniques. So you can hope that in the regime where Delphin was working, so the regime where the total weight is growing as a polynomial, you have you get something reasonable by doing this heuristic. I assume that capital WN is growing like.
Sorry, Michel, could I
Yes.
just ask about the analogy? So what are the particles meant to represent, and what are their positions meant to represent?
Position would be the height. No, of course, it's okay. Really, you want to see the positions as the heights of the particle, and at time t here, you will have roughly n particles, and when you pick one uniformly, its trajectory will be given by this sum of Bernoullis. So I want to say it's the same. And the fact is that it works. I mean, it gives exactly the same quantities. It works pretty well to predict. Okay, of course, it's very, here in the tree, particles are never disappearing. Here, somehow they are disappearing. I don't say it's quite the same, but it's working. That's my claim. It's a good heuristic just by the fact that you get exactly the same results for the tree. Yeah.
Sorry, to follow up on Sarah's question, you get the same results for the height or for the tip distribution
for
of
the height,
but not for typical particles or degree distribution or things like that.
No, I don't think. Okay, degree distribution would have not a lot of mean in the branching random walk. That's not what I claim. Yes, I'm really thinking about the height.
Okay, thank you.
Okay, maybe another way to see it is that, okay, how do you get the height? I said that the height of one vertex, the vertex number n, typically it's a Gaussian distribution centered at an, but you are doing this many times, n times, so it's a large deviation event, which gives you the particles where you are going very high. And I claim that it's the same event as the one which are going to the top here, not the same. Okay, it's working exactly in the same way. Okay, let me state the result. And okay, my claim here is to say, okay, now let's assume that you are more or less growing like this. So it means that an behaves like gamma log n. So here you can plug this in here, and it means that in my branching random walk, the jump at time s will have the distribution which is Poisson with parameter gamma. So one remarkable fact is that if capital Wn is growing polynomially, it's exactly the same as saying more or less that an is growing logarithmically. And the case where an is growing logarithmically, exactly the one where here you get a constant which does not depend on s. So I pretend that because of this, we'll see afterwards examples that show that it should be true, but this is the only regime where you behave as a regular branching random walk. Okay, let me write the result in this case. So the theorem with which is Delphin is the following: the height of the tree is this constant times gamma log n, explained here, and then a logarithmic correction. So it's a logarithm of t, so double log n, plus a tight sequence. So if you look at the branching random walk with parameter mean number of children e and Poisson gamma jumps, you would get exactly the same constants here, which are explicit in terms of gamma. I don't write them, but you would get exactly the same constant. This is branching random walk universality. So I would say it's because of the 3/2. Of course, here I'm a bit cheating because there is another constant C2. So you could say that the 3/2 is a completely, I forced it to appear, but the reasonable thing to see that it's really the 3/2 from branching random walk and also from FKPP, it's the same. So it's a branching random walk universality or FKPP universality. It's because you can compare with the maximum of n copies independent, so ID copies me write independent copies of this of what a particular vertex is doing. You know that the height of the nth vertex is roughly this sum. Let's say that everything was completely independent and more or less you're trying to look at what does n copies of this, the maximum of n copies, independent copies of this look like. It looks like this, the same expansion, but with a 1/2 instead of the 3/2. This is telling you that this 3/2 is really the one of the universality of branching random walks. It's due to the tree structure. Things are not completely independent. At the first order, you see no difference, but at the second order, you see a 3/2 instead of a 1/2. Okay, questions? Small breaks. Okay. Yes, there are solutions of a simple equation stated in terms of gamma. The solution is not explicit. It's not solvable in terms of common function, but the equation is in terms of common function. So it's really the same as for the branching random walk with these parameters, and you can you can compute them. Okay. Okay. So briefly about this, I wanted to say that. So actually two remarks. One is that it was proved for the uniform recursive tree by Luigi, actually. So I have to cite this paper. So it's Dario Berry and Ford in 2013, I think. And okay, for the uniform recursive tree, you can really have rigorous links with branching random walks, which are not exactly the same as this one. This one, okay. I agree that it looks a bit weird, but at least it's good in predictions. So, and also, one natural question is the big O of 1 converging or not? And usually in non-lattice branching random walks or branching Brownian motion, it's converging to a shifted Gumbel. Here, you cannot hope a shifted Gumbel because you, at this level of precision, you still see that you are an integer. You cannot converge to a Gumbel if you are integer valued. And actually, you're not converging to something else. You're just not converging, probably. So, okay, we have not proved it, but the answer is probably no. And there are some rigorous results about this. So really, there is a fluctuation of the law at the tip. And this has been obtained for, sorry, there are two papers, I don't remember the years. Let me add this. By Mota and then by Core in 2017 for the binary search trees. So it's another kind of model built recursively. They obtain, okay, probably the best you can obtain about this big O of 1, which is not convergence, but the fact that you are oscillating in distribution at the tip. Okay. So now I want to go out from this universality class. So now we'll take, so I have two options. Either I can take a total weight which is growing very fast, or a total weight which is kind of small. So that's what I will choose. So Wn subpolynomial. So a good way to state the result is actually to state it in terms of AN. But you have you always have this kind of relation between AN and WN. Up to a small term, depending on some assumption that I'm completely hiding. AN is always like the logarithm of WN plus some constant plus something. Okay, so I will state in terms of AN because it will be much more unified. And at least you can see that WN subpolynomial, it's the same as saying I want AN, which is much smaller than log n. Okay. So the theorem. Assume that AN can be written in the following way. So some constant, I will call it lambda, times an integral. Okay, it's a weird representation at first, but I'll comment on it. Integral of x to the power minus alpha over 1 minus alpha dx plus something small enough. And alpha is something positive. So, okay, why am I writing it this way? If alpha is smaller than 1, then this is not integrable at infinity. So it will grow like log n, or less. AN will grow like log n to the 1 minus alpha if alpha is smaller than 1. But it will also, if alpha is larger than 1, this is just a converging integral. And it means that my AN is converging to something. So it's also mean that WN is converging to something. But it's converging at a speed which is proportional to some power of log n. So this is a concise way to write both things. Either it's growing as a power of log n, or it's converging as a power of log n. Okay, then what is the result? The heights. Okay. Tn. So the first order is log n over log n. So as I claimed that while showing the pictures, this is much larger than AN. AN is either a power of log n or even converging, but still the height is almost log n. So you really have a tree which has a wide bottom, and then it's going very thin to a quite high height. And then what is the correction? So first it's a plus, not a minus. It has nothing to do with this. It's not much smaller. It's actually log n over alpha log n squared. And actually there is, okay, that's where it's starting to look a bit ugly, but okay, let's write it. At this next order, so I divide once again by log n. I have one term of size log n, and one term which is an explicit constant of alpha and lambda. Actually, we could compute the next terms, but okay. They are all a bit like this with powers of log n. And, okay. So yeah, stop here. I change the board. Questions about this before I change the board for the Zoom audience? I will make a brief pause. So one interesting thing that I'm going to do right now is compare with IID random variable. What would we get if we were taking IID random variables? Okay, I'm seeing that I'm running a bit out of time. I have to change the board. Is this regime particularly interesting, actually, to our own opinion? I don't know for you, but it's that we can see the transition in the, if you compare with the IID case, So I decays, I mean by n copies of sums of Bernoullis. And the difference appears at the third order if alpha is between 0 and 1. At the second order if alpha is equal to 1. And at the first order if alpha is larger than 1. Okay, so kind of see the transition of the effect of so the fact that you have a difference between the result for the tree and the result for ID random variables shows how strong are the correlation due to the branching structure. What I'm saying is the smaller the weights, the higher the correlation, because kind of everything is happening at the beginning. And here you have this transition where depending on alpha, you can see that the effect of the branching of the hierarchical structure is stronger and stronger. Okay, and I'm almost out of time, but I want to conclude by comparing with by doing again my branching random walk analogy. So I said that my jumps at time s have roughly the same distribution as a Poisson with parameter a taken at time exponential s plus 1 minus a at times exponential s. And here you can compute, it gives you the integral of x minus alpha between these two times, and you will get a Poisson random variable with some the constant which appears here, but most importantly, you get s minus alpha. Okay, so this is a time-inhomogeneous branching random walk because the law of the jump depends on the time. So this type of random walks have been studied. So we talked about it just during Jason's talk, for example, by Pascal or by Bastien. Here, it's not the same framework as the one where they studied this model. So the model where the framework where it has been studied was introduced by Bouvier and Kourkova, inspired by the generalized energy model introduced by Bernard. So I think it's 2004 or something like that. And here they say fix an horizon t, and then jumps are so let's say Gaussian with some function of s over t. You take a profile of variance, let's say decreasing. Here everything is decreasing, but fixed. I don't know, like this, for example, between 0 and 1. When you say the variance at time s for a fixed horizon t, it will be given by this function at times s over t. So here, this is really a model which is always defined for each fixed horizon t. Here instead, the variance is decreasing over and over because it's defined in a consistent way. So it's kind of not the same class of universality. And okay, I think I'm over. So I will just say that typically here in this case of so I won't even call it a class of universality in this case. It's really strongly dependent on the law. Here, for example, if you replace by normal distribution, you get something completely different. Because here, typically, you ask to do very large deviation events where you have no universality at all between different jump distributions. And but at least you can use this to kind of guess this formula. It works. Okay, I will stop here because I'm already out of time, I think.
Do we have questions for Michel?
So could you give us, maybe this is not possible, but could you give us some intuition for why, for example, you get the change at the first order for alpha bigger than 1? Is there some way to see that it should make more of a difference moving between the IOD and the actual model?
Um,
Sorry, maybe that's an impossible question.
okay, I don't see any easy argument to see that it happens at which order it will appear.
Yeah, I mean,
no.
it's just very interesting that you have these three different.
Okay, I would need to think about it just a bit more, but.
Could you give us some insight in the proofs?
Yes, so
Thanks.
that's what I had no time to do, but okay. The two main tools are many-to-one and a many-to-two lemma. The many-to-one is more or less the one I presented for the height of the nth vertex. From this, you are able to compute first moment of some quantity. And they are expressed in terms of this random walk with jumps bi. And then you have a many-to-two lemma. So you can pick two vertices uniformly in the tree, not uniformly, but according to their weights in the tree, and look at their how their ancestral lineages were growing. And they are growing as this random walk, but which is completely correlated at the beginning, and then more or less independent. So in a branching random walk, usually in the many-to-two, you're completely independent once you have branched. Here, it's not the case because if you are looking at the proof I made, if you put a vertex in one of the lineage, you cannot put it in the other one. So if one of the random walk is jumping at some time, the other one cannot jump. So you have very weak interaction between the two walks. So here you have a many-to-two, which looks like the one of the branching random walk, but with some interactions between the walks, which are tractable, let's say, and they do not have an influence. So the proofs are you have to use this many-to-one, many-to-two to compute first and second moments with barrier, very similar to branching random walks. Maybe one difficulty is that you don't have a branching property. So if you're stopping, you're looking at your tree after adding, I don't know, 5 vertices, and then you look at the future. The future of each vertex depends on the future of the other ones. I mean, if you have a vertex with a very large weight, if it's attached to 2, it's not attached to 3, and it has an influence in the future. So you don't have the branching property, but okay, you can deal without it. I think that's more or less the. So it's for example, branching random walks techniques have been applied to log-correlated fields where you don't have the branching property and you can still do things. So it's kind of the same framework, I would say.
Can you say something about the colors in your tree, like maybe saying things about when does the maximum get reached, like as the maximum at time n? I guess it's from a vertex that you put at some time that was very close to time n. Can you say how close?
So okay, can you repeat? Are you talking about the colors which were in the
yes,
picture?
or the name of the vertex that is the maximum at time n, for example?
Oh. So for sure, okay, there is maybe something which looks strange in this analogy, which is that this was for vertex number n, but maybe not for vertex number n over 2. And when I say I'm compared to n independent copies of this, you could say I'm cheating. But actually, you can, in all the regimes I was talking about, you can look at the sum between n over 2 and n of all these Bernoullis, and they are more or less at most of mean 1. I mean, there are the parameters of these Bernoullis are smaller and smaller. So actually, all the last ones, they are, the top does not necessarily has a label which is of order n, for example. That's not true. So okay, here the colors in my tree are probably not put in the right way to answer your question. Actually,
so can you say of which order is the top then?
Okay, not much less than n, probably not. Okay, maybe it's of order n, but really you can take some epsilon. It's between epsilon n and n with as epsilon goes to infinity, it has a probability which goes to 1 to be there, I would say. Okay, that's my guess, but really a wild guess.
Okay, let's thank Michel again.